All right, here we're going to walk through our group work on functions of several variables. First one, we got a mix and match, a number of different functions. I want to just play around with them, explore a little bit, and see which one of these graphs match up to which of these functions. So we can just pick up a few observations about each, and that should be enough to narrow down what these could be. So starting with function A, I got a sum of two absolute values here. One of the things that we can notice from this is that, well, absolute values are always greater than or equal to 0. And so this thing is going to be always 0 or bigger. And in fact, the only time that we'd have this equal to 0 is if x and y are both 0. Right, if either of them are non-zero, then the absolute value will give us something positive, and we'll be adding something that makes that stay the same or get bigger. So this thing's only 0 at the origin, and so looking down at our graphs, this is not 0 at the origin. Looks like this maybe has a line where it's 0, 0 a whole bunch, some lines where it's 0, 0 along the axes. Looks like 6 is our winner for A. All right, what about B? Another absolute value, but here we have a product, x times y inside the absolute value. So this absolute value is going to be 0. We can think about that once again, the whole thing. It's going to be 0 when what's inside is 0. X times y equals 0. Since that's a product, this is when x equals 0 or y equals 0. So we actually have both of our axes, our y-axis and our x-axis, should be zeros for our function. And so looking at our graph here, the only one that matches that description is over here. Function number 5. I think they should write a song entitled Function Number 5. All right, C. Looking at our function here, it's a rational function, and we 1 over 1 plus x squared plus y squared. One of the things we might be able to notice right off the bat, if we plug in x and y equal to 0, let's see what's happening at the origin. We're going to get 1 over 1 plus 0, so 1. And looks like that eliminates function 4. Function 3 might be okay. Function 2 is out, so function 1 or function 4 perhaps. But notice if x or y, if those get big, our denominator is going to get big here, and our fraction is going to get smaller. And so here, this one, number 4, looks like it's kind of where we can move off in some directions where it gets big. I don't think C is going to have that behavior. Looks like number 1 is our winner. We're moving around in any direction. And our z values are getting smaller and smaller. Looks like that is our winner for function C. Function D, polynomial. Nice question here is, well, when is this thing equal to 0? Well, this thing's going to be 0 when what's being squared is 0. Actually, if we work this out, x squared equals y squared. If we take the square root of both sides, we can get y is plus or minus the square root of x squared. So we can just leave that as plus or minus x. So we actually have two diagonal lines in the xy plane that are going to make our function 0. And looks like function 4 has that. Right, there's our y equals x line, there's our y equals negative x line, giving us 0 z values for our function. And so 4 is function D. Over here, E, a similar game here, shows that f equals 0 when x minus y equals 0, i.e. when y equals x. And so here we only have one line where this thing's 0, and that looks like this one over here, right? Only 0 along that diagonal line, y equals x. Function 2 is matching up with e. So last but not least, f is this weird sine function. Not too surprising, right? We should see some oscillations going on, and we do indeed at 3. Interestingly, our function f takes our function a down here and tosses those outputs into the sine function, right? So this is like our function a, and then tossed into the sine function, and then there's what we get, function f. Or I guess graph 3. There it is. All right, moving on down. All right, in problem 2, we're playing around this particular function, f equals y squared plus 1. In problem 3, we're looking at domain. I have a sheet prepared. We'll walk through those solutions. All right, so for number 2, looking at this function, we want to sketch its graph, find its domain and range, and sketch the contour plot. I think it might have been a different order. What did they say? Domain and range first, contour plot second, sketch the graph third. We'll do it that way. All right, so domain and range. So you're looking at our function. It's polynomial. We can plug in any x and y we want. It doesn't even use x, so x is not going to mess it up. Neither is y. So the domain here is all x, y, i.e. r squared. Right, that's the full xy plane. For the range, y squared, it's always bigger than or equal to 0, and so plus 1, this is always bigger than or equal to 1. And we can get the z value of 1 if we plug in y equals 0. We'll see 1 as the output, and if we increase y as much as we want, we'll get any z value we want higher than that as well. So our range starts at z equals 1, and we can get anything past that as well. So that interval from 1 to infinity, or you can write that as z greater than or equal to 1. All right, for the contour plot, we can pick some different z values. Notice if we pick something like z equals 0 and plug it in, right, for our function, right, function is telling us the z values. We're going to get from the equation, so 0 equals y squared plus 1, which hands us negative 1 equals y squared. So that doesn't have any solutions, so that's a whiff if we try and cut at z equals 0. And similarly, right, essentially because of the range here, bigger than or equal to 1, anything less than 1 or anything negative, we're also going to get no solutions. All right, but we'll start seeing a solution at z equals 1. If we plug that in for our function here, we get 0 equals y squared, which boils down to y equals 0. And so that is the x-axis. So that's the level curve for z equals 0. Out about z equals 2, if we plug that in, it boils down to y is plus or minus 1. And so now we actually get 2 curves, each corresponding to the elevation of z equals 1. And similarly, we could keep on going. Here I have z equals 5. We can maybe work that out here. If we did z equals 5, right, we get 5 equals y squared plus 1. So y squared equals 4. So y is plus or minus 2. And we're seeing that here. All right, so there's, again, 2 curves where we have that same elevation of z equals 5. Kind of see that as we increase z, we're going to get, again, 2 lines that are going to be spreading out more and more. A couple different ways we could think of getting the graph. One is just by looking at the equation. We replace f with z. And this is the equation defining our graph in 3 space. And notice it doesn't involve x. All right, so this is a happy situation where we can just graph this in the y-z plane, and we get a parabola pushed up by 1, and in 3 space, right, it looks like this. Here's our parabola. And then we're just going to extend that forward and backward perfectly in the x direction, giving us this big old infinite half pipe. On this picture, we can also see our level curves. If we bring those out of the xy plane where they naturally live, we can see those here in 3 space. Right here is our lowest z value, z equals 1 at the bottom of the half pipe, and then coming on the side, we'd get the z equals 1. And then moving along, there's our sum. Let me try that one again. Z equals 2. There and there, perhaps. Right, and spreading out if we increase that z value. All right. For number 3, we're looking to take this crazy looking function and find its domain and sketch its domain. Right? And so notice this is a function of 3 variables. And so this function takes in an xyz point and spits out something else, w. And so its graph would actually naturally live in 3 space, or not, 4 space. I was just thinking, a function of 2 variables, its graph naturally lives in 3 space. A function of 3 variables naturally lives its graph in 4-dimensional space. So we can't really graph all of that at once, but we can sketch its domain in 3 space. All right, we can just look at the different pieces of our function and see what is required. All of our square roots, whenever we have a square root, right, we need what is inside the square root to be greater than or equal to 0. So we need x, y, and z, all of those bigger than or equal to 0. So we're kind of looking at the first octant at this point. But what about the natural log? Well, natural log, we need whatever is inside of that to be positive, right? Can't plug in 0 or anything negative to natural log, so that had better be positive. So that gets us our other inequality over here. And if we want, we can take all of our variables and toss them to the other side. We get 4 is greater than x squared plus y squared plus z squared. Here to get a sense of what this is, imagine this inequality was actually an equality. Well, this would be giving us a sphere centered at the origin of radius 2. And that would be the outer shell of the sphere. But since we want the x, y's, and z's that make this expression less than 4, that's going to be the guts of the sphere. So if the sphere was an orange, right? We don't include the peel. It's just the juicy goodness inside. The guts of the sphere, the stuff inside. And that's what this is describing for us. And so if we put that together with our other observations, restrictions on x, y, and z, right, we are in the first octant, and we are looking at the guts inside the sphere of radius 2. So here I've kind of drawn the shell of the sphere, dashed lines, and we're looking at the stuff inside. So anything in this this chunk we could plug into our function g. That is its domain. All right, that's it for today. See you next time.